Okay, we're going to do a video on centripetal acceleration. This is 4.5. I would do more for this lecture, get you started on forces, but forces are a lot for that Wednesday lecture. I'm going to do a lot of things on forces, but I want to finish up chapter 4. Last time, we talked about things involving angular motion. It's kind of rough sometimes. Uniform circular motion, so circumference all the way around the circle. These are things moving in circles. Things tend to move in straight lines or circles or combinations of both. Depends. Things can move in ellipses, but those are our models that are simplified versions of reality. Of course, how fast you're moving around it, like on a speedometer, that's your circumference over the period. We talked about the angle change is in degrees, and we think of that in radians. You do degrees, but how much angle changes? A radian, 2 pi radians is all the way around. That's our definition. So 2 pi is all the way around. Of course, the definition of an angle is basically that arc length there times the rate divided by the radius of that motion, which you can basically change that to S equals r theta, or arc length equals radius times how much the angle changed. And that makes sense. If the angle changes more, arc length is more. If you got a longer radius, bigger change in arc length out there. We did angular velocity, and we said that's equal to how fast the angle rotates. And that's basically d theta dt, or the change in theta as a function of time, how quickly the angle changes over time. And that's angular velocity. We didn't really talk anything about acceleration here. We did do the relationship between velocity and angular velocity. And the relationship there, of course, is v equals omega times r. We derived that. It lasts a little bit. I want to talk about centripetal acceleration. I'll mention angular acceleration in the end. That's one section we're not going over, but it is in the lab, so I want to go over that, help you be able to do that part of the lab so you kind of understand it. It's pretty simple, honestly. Let's look at 4.5 centripetal acceleration. And the book does a decent job here, but there's some videos I put up on there. There's a third one that really shows the direction of centripetal acceleration. And what I want to do is, to some extent, derive it. And but I'm going to derive it using vectors. The book goes through and does an algebraic derivation, and look over that and to see where the equation comes from. I'm going to look at it from a vector sense so you understand direction. I can derive the equation where it comes from, and then you're okay. But the direction, people tend to have trouble seeing this. Now, what's centripetal acceleration? It's how objects in circular motion change their tangential velocity. Okay. It's tangent. It's really, honestly, so easy to explain if I could use forces. But I haven't talked about a force yet, so I'm not going to go into explaining really why here. But when you think of circular motion, my arm could be a string, and this could be a rock. It's a rock that says great erase bold big. Bold color dry erase marker. Well, this is our rock. And as I go around and around with it, I'm accelerating the object. Now, you would say, I'm trying to keep it at a constant rate, but it's not. But let's assume I could. I keep this at a constant rate going around and around. Definitely demonstrates a ball and socket joint in your shoulder, right? As it demonstrates that going around and around, is it speeding up? No. Is it slowing down? No. If I can keep the tangent, if I can keep the speedometer on this thing going at the same number. It's like racing and you're going 100 miles an hour, turn left. But the speedometer doesn't really tell us velocity. It only tells us speed, the magnitude of the velocity. We said earlier that you can accelerate. Your car had 3 accelerators: the brake, the gas pedal, and the steering wheel. So if I change the direction of this rock, this dry erase bowl blue rock, I'm also accelerating it. So hopefully that makes sense the way we define velocity, how fast you're going in a certain direction. Acceleration is how much your velocity changes. In other words, how much your speed changes. But you also have to say, and or the direction changes. If you do either one, you accelerate. So I am accelerating because I'm changing the direction of my rock. Now let's think, how can we determine the direction of that acceleration? Well, let's look at direction of that acceleration. So acceleration previously would be the change in velocity over change in time. So it's v final minus v initial vector over delta t. So what I'm going to say is that the acceleration vector is in the direction of the, since time always marches forward. Gotta get used to this new height there. Is in the direction of the change in velocity vector, v final minus v initial. So if I do the operation v final minus v initial, if I physically do that with the vectors, I can get the direction of that acceleration. And it makes sense if you think about it. Say my initial velocity is this way. Okay. So velocity is this way, and then that's my final one is this way. Well, if I'm pushed this way, let's just nix that. I can't erase it. Well, I could, but I'm not going to. I'm not going to cut. Let's cut that from my memory. Let's just do the operation, okay? So for circular motion, we'd have, that's like my arm. Here's the rock. Thor's hammer. Am I pure enough to lift Thor's hammer? Maybe I am. Maybe I'm not. But Captain America, some other ones read comics, but in Marvel, in MCU, he was the only one that was worthy besides Thor. So Thor is with, Captain America lifts a hammer and he starts spinning it around, as he did in Endgame. So it's going in this direction. So if you think about it, let's start off here. That's my initial velocity. A little bit later, say right here, this is going to be my final velocity. These are all vectors. So I've got to take these two vectors and subtract them. So let's blow that up. So tip to tail method, right? Now if I add them, it would be like this. So I'm going to keep these the same distance. So let me make that a little bit longer. Okay, so V final, so that's going to be like that. Tail minus V initial. Now, I would normally stick it here, right? That's the same length. But I can't draw it in that direction, because that would be adding it. I got to subtract it, so it's going to be going the opposite direction. This way, what's the opposite direction? Back the other way. Okay? So here, I'm going to put it here. Let's just put that there. So this is V final. This is minus V initial vector. Now acceleration then, it's going to be in the direction of these two sum up. Now we do tip to tail, here to here. Well, that's in that direction. This is delta V vector. Well, if this was the center here, this is the center. What direction is that? Does that look in the same direction as my arm? It's pretty darn close. What's my ability to draw on a board? Yeah, we can graphically do it, all of that stuff. But that's pretty darn close. It's in about the same direction. And no matter where I would go, that's what would happen. On the book, they use, this is figure 427. They explain it in the book using this technique, figure 427. I just kind of did it on the board, drawing it out for you. So the change in velocity is in a direct, which is the acceleration, is in the direction of the radius. And where does that radius end up at? At the center. So the big swerve here, something you might not think would happen, is centripetal acceleration is toward, and that's what this is right here. This is going to be acceleration for circular motion, is toward the center of the circle. OMG. Oh. Now it makes sense if you think about it. If I'm spinning something around, got my rock again, right? Now I'm spinning around and it's right up here. Which way is that rock going to go? I'm going to do it this way because it's easier that way. So if I'm spinning it around, if I let go here at the top, which way is it wanting to go? Oops, I hit the projection screen there. It wanted to go straight out that way. What if I let it go right here? Which way does it want to go? What's its velocity? What's the direction of its tangential velocity? Down. It wanted to go downward. What direction must I pull on it? How must I affect it to make it keep going in a circle? Well, if it's wanting to go this way, which way have I got to pull on? Which way am my arm pulling on it? It's pulling it down. If it's right here, which way is my arm pulling on it? I'm pulling it this way. If it's right here, which would make it want to go into the board, onto the wall over there, it went that way. Which way have I got to pull on it? Which way have I got to affect its motion? I'm going to do this way. Here, it'll go straight up. I'm not going to do that one right now. So my arm is the agent. And we'll talk more about that later. Not the 007 agent or 007. But it's what affects that motion. It's what makes the object accelerate. Changes the motion of an object to make it go in a circular path. So if you do circular acceleration, centripetal acceleration, the fancy name we use, it's just acceleration to make something go in a circle, and the direction of that to make that occur has to be toward the center. Because we're all the time trying to overcome the direction the thing wants to go, the rock wants to go, which is its tangential velocity. It's the tangential velocity. Okay? It's toward the center of the circle. Big idea. Of course, a big idea, you know it'll be a big something on the test. Okay? Now, the question is, how do you calculate that then? We got the direction. What's the calculation? The book goes through a derivation. Go through it if you want to see where it comes from. They do something very similar to what I just did here. We'll look at it more analytically. I will state that the acceleration is equal to v squared over r. and it's in the direction toward the center of the circle. And using our hat notation, which we developed in chapter 3, you could say that this is equal to v squared over r hat. And that's our unit vector notation, because r hat then is, it's a unit vector. That means it has a magnitude of 1. It's in the direction of, as you probably guessed it, radius. In the direction of the radius. And if you think of it like that, you actually have to put a negative in here. If you think of it like this, to write it with just this notation, because r, the radius goes outward. And so how can you make the direction towards back the other way? You have to have the negative of that unit vector. Now, could you define the unit vector to be inward? You could, but for stuff, when you do spherical coordinates, for stuff you'll do later on, you'll see that's just not the way mathematicians and physicists decided to do it. They always have it, as its magnitude, its direction of it is always an increasing radius or increasing angle. You do the direction of the unit vector in the direction of whatever you're talking about increasing. That's why, so this would be an increasing radius, so it has to be outward. That negative then means the direction is inward. Okay? Alright. So they do I want to say model 4.2 summarizes section 4.4 and 4.5 well. Put it in your notes. Model 4.2. Put that in your notes. I can put it on the board just as easy as you can write it down and put it in your notes. So it behooves you to put that in your notes and go through and write it down and get the gist, get what that is saying. Okay. Some example problems. They do acceleration of a Ferris wheel. Let me do that one, because that's actually a 2-step problem here. And actually it's a little bit more than that. But let me do that one real quick for you. Get an idea of how you're going to do these problems. All right, so anybody want to read it? You don't know what I'm doing, so you're watching the video. So I guess I'll be the one. And see, I can wear the shirt, and I can work at the carn, be a carny wearing this shirt, right? Yeah. A typical carnival Ferris wheel has a radius of 9 meters and rotates 4 times per minute. What speed and acceleration do the riders experience? So let's draw our picture. So this is an example 4.12. And so you've got a Ferris wheel. So you got people on the Ferris wheel. It's so lovely, you go to the fair, we can't have those because of the virus, but when we used to, you'd have it, and maybe we'll have them again. You go to the fair, you're sitting there with your family, your friends, your date, whoever, on the Ferris wheel is going around, right? Alright. So, the radius here, 9.0 meters, and the time all the way around, about 4 times, 4.0 times per minute. All right, we want to know, so our radius is 9.0 meters. Our period, well, that's what time around is, a period We'll say 4 times per minute. We got to convert that to something though. Period for, this is 4 rotations. That's not really a period. A period is for 1 rotation, right? Alright, and we want to know our velocity going around, and we want to know the acceleration going around. So this is like a tangential velocity. Okay. Well, first of all, let's get this figured out, okay? So that period 4 times a minute, probably want that in seconds. So if it's 4 times a minute, that would be 4.0 times in 60 seconds. So that's 1.0 times, reduce the fraction in 1. Or divide 4 to 60, however you want to do it. In 15 seconds. So what does that really tell us? That the period of 1 rotation, and this really wasn't a period. We got to call this something else. This is just time, rotation rate. It's really rotation rate. And we're just using kind of logic and common sense to figure out what the period is for 1 rotation is. 1 rotation is going to be 15 seconds. Now that's what we want. Because we know the radius now. And we want to find the tangential velocity, how fast you're going around it. Well, last time we said, as I reviewed a little bit beginning, that velocity is just equal to, it was distance over time, and the distance all the way around is 2 pi r, we said, and the time all the way around was the period. That was from the previous lecture, beginning of section 4.4. Well, do we have the radius around? Yes. Do we have the period? Yes. Now we can do this. So 2 pi, radius is 9.0 meters, over 15 seconds. Well, 2 pi is 6.28 times 9, so that's about 54. Let's see, 9 times 0.28, 54, that's about 57, about 15. It's a little bit less than 4. It's going to be what, 3.8 to 2 sig figs. That's right. 3.8 meters per second. So that would be your velocity as you go around it. Okay. Questions? You don't have any, because nobody's here. But I can pretend. Yes. Okay. Where did this come from? That's a circumference. So all the way around, I have to take all the way around as your distance because that period is all the way around in time. If I did half of the time to go halfway around, I'd have to take the distance halfway around. Remember, velocity, by definition, is distance over time. Changing distance over changing time. So I just took this as for 1 full circle and the time for 1 full circle. Okay? I hope that helps. Let's look at the acceleration now, the centripetal acceleration. Jeez, we know that's v squared over r. And we know r, we know v. Ah, diggity dog. I could do the Mickey Mouse. Hot dog, hot dog. You guys know that dance? I bet Paulus knows that dance. Jonathan Paulus. Percy, I bet, does the Mickey Mouse hot diggity dog dance, don't you, Percy? Bet you do. You don't show anybody or tell anybody about it. Bet you have as a kid. Alright. 3.8 meters per second, quantity squared, over r, 9.0 meters. Okay. And 3.8 squared, 4016, so that's probably, let's say 1500, or about 15 divided by 9. So about 1.7. This would be meters squared over seconds squared, and might cancel more than meters per second squared as your units. And I said 1.7, 1.6, dang it. Oh, it's going to get better doing stuff in my head. 1.6 meters per second. And of course, that's the magnitude of that centripetal acceleration. Of course, the direction of it is towards the center of that Ferris wheel, along the radius. Okay? That's the way you would do these problems. I've done a variation of David's sling using this problem. Once we get the forces, we can really do a good problem with David's sling. And, knocking down the giant. And there's lots of different things you can do with this. We can create, I guess, a superhero. If you watch about the soups on The Boys on Amazon, if you watch that one, we can create a character, and we can do that. Because they just came out with like a guy named Eagle who shoots bows and arrows all the time. You got basically a Hawkeye type character on that. That's what have a guy spinning a sling. Same thing, I guess. And you need to calculate velocity and acceleration. Velocity would be neat, because that's how you need how fast that rock or whatever's in that sling as you spin it around is going, and then when you release it, it's going to be hitting that. And that's going to know your acceleration. I will tell you just a little bit ahead of time. That also allows you then to find the force you've got to exert to do that. I do want to go over one thing in the book on the next section under 4.6. This is on non-uniform circular motion. This is when circular motion changes as it's going around. It changes speed as it goes around. Anything that changes speed as it goes around, that means it's going to be, its magnitude is changing. So that's going to be accelerating there, but that's not taking into account direction. I mean, that would basically tell you how much the angle changes as a function of time. And centripetal acceleration assumes, your speedometer or how fast you're going as you go around is constant. It just shows when that's occurring, the centripetal acceleration towards the middle. What happens if I'm doing, which is actually almost like the orbit of comets around the sun. That's elliptical, but the same idea applies. That's sort of where I'm moving fast here in a circular motion, but moving slow up here. In that case, then the angle is changing. How the angular velocity is changing as a function of time. And we use something called alpha. We call that the angular acceleration. And this angular acceleration alpha is the Greek, it's A, Greek letter A, alpha. And of course, acceleration is Greek. All right. That angular acceleration is going to be the change in omega over the change in time. Or from a calculus perspective, of course, it would be in the limit as these deltas get really, 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 really small. You can't really see this change, but you know it's there, but it's so small you can't really see it. And in the limit, as that change approaches zero, we make this change so small, we call it a differential. d omega over dt. This would then be angular acceleration is the derivative of the angular velocity as a function of time. If you remember derivatives, which are just rates of change, if this is constant, if omega was constant, that rotation rate is constant, then angular acceleration alpha would be zero. But as the rotation rate changes, now we've got an angular acceleration, but the centripetal acceleration is always towards the center. There's always a centripetal acceleration. So moving at a constant speed like this, just centripetal acceleration. When I'm doing this, the rotation rate is changing. I also have a centripetal acceleration, which is the direction of this, and I've got an angular acceleration. So I basically got two accelerations going on. We're not going to get into adding those. That's way beyond what I want to go into. The lab talks a little bit about this. I just want you to know that the angular acceleration is really the change in the angular velocity as a function of time. So you kind of know what that is, and there's a little question on the lab about that. And graphically, you should be able to see that. Okay. So that's circular motion, and I hope that's good for you.